Today's speaker is here. Dr. Xudong Fan will talk about his research about AI for networked infrastructure systems. Dr. Xudong Fan is an assistant professor in the Department of Civil, Structural, and Environmental Engineering from the University of Buffalo. Prior to joining University of Buffalo, he was a postdoc researcher in the Department of Civil and Environmental Engineering at Princeton University. He received his PhD in the Civil and Environmental Department from Case Western Reserve University in 2023. He also received his bachelor's degree and master's degree in civil engineering at Central South University and Tianjin University, respectively. His research is motivated by mitigating public losses caused by infrastructure failures, with the goal of developing smart infrastructure systems using computational method and advanced AI techniques. Dr. Fan serves on multiple organizations, such as committee member of TRB and risk assessment and management at ASCE, and young member engagement community at ASCE. Now let's welcome Dr. Fan for his presentation.
Hi everyone. It's very nice to meet you. Let me try to adjust my camera slightly. All right. Yeah. So very nice to meet everyone. So thank you very much for Jiran's invitation. And I was supposed to meet with everyone in person in April, but unfortunately there is some issues with my family and I have to reduce my travel. But I do miss Florida, especially due to the winter storm now at Buffalo. So yeah, let me share my screen. Oh, I also cannot share my screen.
Let me see if I can.
Yeah.
How do you know how to
make
enable
you a
sharing?
presider.
Oh,
cool. Try again. I just make you presider.
I can do it now. All right. So
good.
Yes, here we are.
Thank you. Great.
Awesome. So yes. So as introduced by Jinran, like my work is really focused on how to combine the artificial intelligence and how to use it for the networked infrastructure systems. As you can see, this idea has kind of like cross-through my whole PhD, my postdoc, and also my current work. So in today, I'm going to discuss with you and also talk about how our research is focusing on the artificial intelligence for the networked infrastructure system. The first, let me see if I can, yeah. So the first section that I would like to briefly introduce is that what AI can do for the infrastructure systems, and especially I will highlight one project that I did before, which is the using the AI for the resilience-oriented network decision making. So regarding the background, I just want to highlight that our urban functionalities, our urban lives are actually supported by a large scale of infrastructure systems. Particularly in the US, we have more than 4 million miles of public roadways, more than 5 million miles of powers, and also more than 2 million of pipes, and also 600,000 bridges. So these large-scale infrastructure systems together support the daily functions of our urban livings. We have, with the time going by, especially most of the infrastructures are built maybe like almost like 100 years ago. The aging infrastructure has results in a significant economic loss and even fatalities. This is the left image is a bridge collapse in Pittsburgh, which is quite famous back to like 3 years ago when there is a president debate in Pittsburgh and the bridge just collapsed. A president visit at Pittsburgh and the bridge just collapsed like 1 day before the event. And you can see there are several buses are falling down to the under the bridge. And also in the daily life, if we look at the water main break, you can see that So the significant loss of water from the water systems can also cause the flooding issue and interrupt the traffic. So always the failure of the infrastructure will always have like direct and indirect failures. If we look at the condition of the United States infrastructure, so I'm showing the AICE infrastructure report card, which is updated every 4 years. So I happens to have the 4 years, which is the 2021 grades and also the 2025 report card. Well, most of them are not changing much, but you can see the overall condition is not great enough. So the condition A, the gradients will range from the A to F, where the A is exceptional, meaning that's the best condition, and F is of course the failing condition. So you can see the majority of the infrastructure that in the states are falling between the category of C and D. And I highlight a few infrastructure here, such as the drinking water, energy, roads, stormwater, wastewater. There are actually more the other infrastructure systems, such as the transit and they are, you can imagine that they are networked systems, meaning that when we're trying to find a better way to manage these types of systems, we usually like to highlight this system as a complex network instead of the structure components. So with that saying that my research, especially and also my current research, is really focusing on what we call the underground infrastructure and focus more on the water pipes. But if you look at this image here, it's actually we have a very crowded system underground. We have the power cables, we have the drinking water mains, we have the fiber cable. Excuse me. We have the fiber cable used for the communication, and on this side that's not covered by the image, we also have the gas main, sewer mains, and also steam lines. So this part is usually used for the heating. So as you can see, there are multi-layer infrastructure systems just under the road. And if we look at the surface of the road, we of course have the road networks. So meaning that there is, we are looking at not only a single type of networked system, but also a multi-layer networked systems. And together they build like the modern communities and the urbans. So back to the management of the infrastructures, there is, if we look at the life cycle of the infrastructure systems, we can conceptually show a map like there is a normal stage and a hazard stage, right? So if we look at this, if we think this y-axis represents the system performance and the x-axis represents the time, we usually can see that the performance of the infrastructure systems will gradually decrease due to the deterioration or due to the component failure. We also have the repair activities that can bounce back the performance. But when there is a hazard happens, there will be a significant and sudden drop of the performance. Of course, we need to recover the system by trying to find an optimal recovery path so that we can fast and effectively recover the system performance. So basically, we are trying to look at this upper convex curve here. Sometimes we like to also to generally say that we have a sustainability part and a resilience part, but this is not very scientific and rigorous. Like sometimes the resilience part will also include the pre-disaster part, but it's again, this is just like a conceptual curve map. So my previous work, especially when we think about what AI can do for the infrastructure, we generally think there are 3 main directions that can be do. For example, AI can be used for the failure prediction, so that we can enable the proactive maintenance and reduce the loss of the infrastructure failure. It can also enable us to do the data-driven health monitoring, meaning that we can know the real-time condition of the system by deploying the sensors into the system, such as the traffic camera for the road systems, or like a pressure sensor or flow rate sensor that is used in the water systems. And together with the failure prediction and the system sensing, we can also think that AI can be used for the decision making, like how we operate the system, how we maintain the system, or how we should repair the system. So in today's talk, we are going to focus more on this resilience-oriented decision making. But if you are interested in any other part of what AI can do, you're welcome to discuss it after the talk. So why the decision making in the large scale infrastructure systems is important is mainly because when we have a nature hazard happen, such as the flooding, as you can see from the image, there are usually a multiple components failure at a larger scale infrastructure system instead of a single structure component failures. And in order to recover the function of the system, there is a need that we want to have an optimal recovery path, like we introduced before. However, there are several challenges here. For example, if we are talking about like hundreds of road segments or pipe segment failures, the combination, the potential repair sequence could be millions of possibilities, meaning that this is a non-determined optimization, and also the possible decisions or repair sequences can be exponentially increased with the number of failure components. And also, we should also think about that each edge will have the importance of the importance of each edge in the graph is not equals. Like it's more like the edge located at different locations, it may have different importance regarding the network connectivity or traffic flow, or also like the water flow. So the network redundant and also the graph structure should rarely be considered in our decision-making process. And of course, the system is dynamically changing. There is nonlinear mechanisms. For example, we need to consider the water flow, which is governed by the nonlinear hydraulic equations. If we also want to consider the traffic flow, it also has nonlinear represented, which add another layer of the complexity when we make decisions. And of course, the last challenge is that when we have a hazard happens, we will always want to have a fast response. We usually do not have the time to do the simulation, to try all the potential decisions, build the simulation model, and identify the really optimal decision. So the fast response is actually quite critical when we are trying to recover the system after the hazard. So here is what we do for solving this task. We want to propose a decision-making method, especially AI supported decision method that to support the recovery decision when the hazard happens. And what we do here is that but in order to test the decision making, we first need to have a virtual test bed. Like regardless of what types of decision we want to make, we need to compare the method on a virtual test bed. And to do that, we actually build two virtual test beds. One is a water system, and we consider the earthquake. So when there is an earthquake happens, there is a fragility curve associated with each pipe, and we simplified a scenario, only want to create a damaged situation of the water systems. The other virtual test bed we build is for the road network together with the flood situation. But for the flood situation, we are actually just we mimic the flooding behavior to the hydraulic simulation, but later we realize that doing the flood simulation is too time consuming, and we then change the failure patterns of the system into the infectious SRI model, which is kind of like an infectious parsing model. It's kind of like a simplified damage scenario model. And then after we have this hazard map, we want to know the component failures, so that we can build this damage scenario like I just mentioned. So for the water pipes, we considered a probability-based damage. That is that by giving the peak ground velocity caused by the earthquake, we have a failure probability of each pipe. And by gathering the failure probability with the pipe and also the length of the pipe, we can sample a number of leaks on the pipe. So by doing so, we are trying to get the number of leaks on each pipe by a given earthquake. So this part is mainly we want to provide a continuous failure scenario that each pipe maybe have multiple failure locations. It can be 1, it can be 2 or 3, but and then for the second virtual test, we are mainly trying to simplify this part and just using a binary failure scenario. That is, each road segment is either open or closed. It is not continuous, it's just a binary scenario. So we actually considered multiple like decision-making methods that try to compare and try to do the recovery process. So in here, as you can see, we consider the AI-based method, which I will introduce in the next slide. That is the method that we developed and proposed. In addition to the AI-based method, I also consider the genetic algorithm, which is also a global surrogate mesuristic optimization algorithm. And also, we can simplify it as an importance-based index. For example, in network, there is a few centrality metrics that can be used as the importance-based index. And also between centrality, that is between centrality can also be used as an importance index. And also we are thinking this recovery as a sequential decision making. So meaning that at each time we only repair one part of the system, like one road segment or one pipe segment in the system, and after repairing. After get a decision about which segment we want to repair, we repair it and conduct the system simulation. For example, for the water distribution system, we reconduct the hydraulic simulation and see how the performance of the system change caused by this repairing. And for the road network, we use the graph connectivity as its assessment. So basically, we are repeating this decision-making and system evaluation process. We make a decision about which part we want to repair, we evaluate the system performance, and we move to the next decision-making, we evaluate it. To quantify the system performance for this water system, we are considering to use this so-called node satisfactory degree, which is basically trying to say how much water can be met based on the needs of the customer. Yes, and these are the equations that are used to do this to do the performance evaluation. So at each step, therefore at each time step, we are able to get the performance index, like measuring the system index, measuring the system performance with a given value. And if we record the performance of the system at each time step, we are able to get a recovery curve, something like that. So, excuse me. So this is our hazard simulation of a pure test bed, how we build it. And of course, if we look at the recovery process, if we consider about the uncertainty, most of the time the recovery might be like a range instead of a single curve. So here is some method, like we consider, again, to be specific, we considered 1, 2, 3, 4, 5 previous methods. Like in here, we have this genetic method. So these numbers are the potential decision sequential. Like assuming we have 9 pipes, and then we do the genetic mutation, and then exchange the decision sequence of of the potential candidates, and then we do this evolution process-based optimization. In addition, we can also do the simplified static importance-based and dynamic importance-based method. So the static importance-based method is basically we are selecting which road segment can achieve the largest performance increasement by comparing the repair of this segment with the very initial scenario. And the dynamic importance based is that at each time step, we're trying to find the repairing decision that can maximize the system performance at this time step. And also the importance-based method, we are using this between centrality. So this is a purely topology evaluation matrix without considering the functions of hydraulic simulations or traffic simulations. So these three methods are the previous methods that proposed in the literature. But what we really want to do here is trying to incorporate the deep reinforcement learning to make the decision. So for the deep reinforcement learning, it is a learning method that's trying to find the value of each decision by a given state of the system. So the idea here is that we have the observation of current state. We know where is we know the failure location. We know the system status. We're passing this current state, let's say, to a neural network, especially like a deep neural network, and let this neural network to predict a sequence of action value, and this action value should match the action value, the space of this action value should match the space of the decision. And if we can find which decision is the most valuable, of course, we can just easily pick the decision with the highest valuable and assume that is our optimal decision. So the key idea of the Q-learning is that by training a neural network that keeps interacting with our previously developed virtual test bed, we are able to consider the short-term reward and also the long-term reward together by using this Bowman equation. But we are not only satisfied with the Bowman equation with traditional reinforcement learning, which is usually represented by several layers fully connected neural network. In this study, we really want to use a graph convolutional neural network as the back end of the reinforcement learning instead of a fully connected neural network. The motivation of using a graph neural network is because, as you can see from the image, the infrastructure system itself is naturally can be represented as network. And we want to learn the geospatial correlation and also the topology structure of the system instead of just using a fully connected neural network. And if we combine the idea of graph convolutional neural network and the deep reinforcement learning, we can get a working flowchart. So we first will initialize our system hazard, like the damage scenario. We will use the AI. We will first let our AI model, which is our graph convolutional neural network. You can see the arrows pointed to our graph neural network. We will use our graph neural network to find the optimal decision and pose this decision to our virtual test bed that developed in a few slides before, and then we get the reward of this decision to see if this decision is good and bad. We will let the AI play with this virtual test bed, like interactively, until that we train our graph convolutional neural network, and it can really learn the value of each decision. So you can see this virtual test bed is functioning like giving the label of a training sample, and then the AI part is really trying to predict the real value of the sample based on this interaction process. What is happening here can be also, if we zoom in, what is happening here, it is our right side. Like, so at a specific current state, we input it into the graph neural network. This graph neural network will embed the state into latent space, which is a super long but no physical meaning vectors of each node. We then can concatenate all the node vectors into an even longer vector and connect this even longer vector as the input of a fully connected neural network. It will try to predict the value of each decision at this time, and then the prediction target will be quantified is the combine of future reward, which is about the potential benefit that the decision can lead, and also the instant reward, which is the immediate reward that this action can lead. These two types of reward is combined by using the Bowman equation that we just introduced in previous slides. And then we will, after selecting the most optimal actions, the system will of course update to the next state, and it will, and this loop, it finished one episode training, and it just keeps interacting until the model, we are satisfied with the model performance. Yeah, so again, if you want to have a highlight idea, it's basically like we have a deep reinforcement learning framework that uses to train a neural network. And the neural network we select is graph convolutional neural network rather than fully connected neural network. So we tested this idea of the framework in two scenarios. The first scenario is a known damage scenario. That is that we have a water distribution system here. We have an earthquake happens, and we know exactly how damage happens at each pipe. So some pipes have like 4 leak points, some pipes have only 1 leak point, but also many pipes do not have any failure. And the left side image here shows the learning curve of our reinforcement learning. So as you can see, each episode here represents a fully recovery of the system. And if we quantified the area of the recovery curve as the performance index of the decision making. You can see at the beginning, the system resilience index, which is the area under the curve, is relatively low. It's because at the beginning, the AI agent is basically just trying to randomly make decisions about which pipe should be repaired first, which pipe should be repaired later. But gradually, with more and more training episodes, the AI agent is learning better and better. And eventually, we can see that the system resilience is pretty high. And it's pretty high. And especially if you compare the recovery curve of these final decisions with the 4 methods that proposed in previous literature, you can see that the curve, the area under the curve of our proposed decision recovery sequence is significant. It's not significant. It's obvious better than the other method. It's better if we think if we are taking as 80% of the system as a part as recovery. If we are thinking about the 80% recovery, we can see that our proposed method can achieve this 80% recovery sooner than any other methods. So we can see that we feel like this decision making is more suitable for can really solve these high dimensional questions. Well, we also want to do something more to based on this framework. The idea here is, so the first case is that we know the exact damage scenario, and then we train a AI agent to make decisions for that scenario. It takes time, to be honest. In order to train the AI agent, we used like 2 weeks to a workstation to train the final neural network that can make decisions. But later we are thinking about, is there any possible that we can train this decision-making agent pre-disaster, like before the disaster really happens, and then when the disaster happens, we can make this reinforcement learning to make decisions directly without training the model. That is ideal because it saves the time. We really have a much longer time before the hazard, but we only have a very short time after hazard before making the decision. So in here, we did this training process and we assume a roads network. Like here, this is a road network here. We randomly create when we train the model, we randomly create damages in the network and then let the reinforcement learning to interact with this virtual testbed. And we train this model even longer than previous work, and trying to let the AI agent to try to see the different, trying to be trained on different types of failure scenarios. And then after train this AI agent, we generated 4 new damage scenarios that have never been seen in the training set. The way that we do that is that we set the random state. So we set 4 new random state, and it generates 4 damage scenarios that have not been seen in the training process. And then we compared our method. We let our trained method directly to make the decisions and compare the performance with the genetic algorithm, which is also a global optimization algorithm, and also the between centrality based prioritized method. As you can see here, from the recovery resilience index, our model, even this AI agent has never seen the damage scenario. It can still make decent decision that achieve a better resilience index compared to the other traditional method. And especially if you look at the time, like for each scenario, our model can make decisions under like 100 seconds. So it's super fast because there's no longer any training process. There is only forward prediction decision-making process. It's super fast. It's almost the same time of calculating the between centrality of the network. But remember, if you want to calculate the between centrality, the computing time will also increase with the size of your network, and this time is significantly much shorter than what we have for the genetic algorithm. The main reason is that for genetic algorithm, there is no transfer learning capability. Like you cannot train, you cannot do this process before you know the damage scenario. You can only use the genetic algorithm after you know the exact damage scenario, and then let it to do this optimization. So genetic algorithm will take, I don't know, is that more than an hour? So which is it's pretty impressive. So it's very interesting. But I hope like, so the previous part is mainly done at the beginning of my work, is that we see the AI is so powerful in making the decision, right? To improving the performance of the system. But later we also want to ask a question, is that how can we make the AI to learn better? We say the learning process of the AI is also what we call the training process. The idea is that we have the neural networks, we train the model, and we get it. But it's actually very interesting, is that can we make the AI learn better? Can we let the AI to learn more effectively for our specialized targets? So the motivation here is that we believe that the feature learning in the neural network is a very fundamental part, so that we need to rely on the learning ability to make good predictions or good decisions. And if you are working with machine learning, you probably are very familiar with this 3-step framework, right? First you have your data collection, you build your data set, and then you let the neural network to learn the feature or learn the pattern from the data set, and project it into an embedding space. And then based on the embedded feature or abstract feature, you do either classification or regression or decision-making process. And this part here is that we really want to motivate, is that can we do a better job for the feature embedding, especially customizing existing algorithm by considering the specific need of the infrastructure systems. So then we are looking at, so motivated by this idea, we are thinking about the most infrastructure systems, or most systems that we as a civil engineer are familiar of, the so-called spatially embedded networks. The reason we call it spatially embedded is because, for example, in here we have the river network, power network, and also road network. These networks are constrained by the embedded spatial environment and the population density, the economic, and also the elevation change of the of the land will shape the structure or topology or connectivities of these networks. So in order to, therefore, in order to motivated by that, we want to have a better network learning representation for these systems. And we realize that the features of each node or edge is actually with different dimensions, right? For example, if we think about the location of each node, it's only 2. It's only a vector of 2. But sometimes we want to consider the regional feature of a node, meaning that we want to see this regional elevation change that this node is centered on, then it will be more like an image, right? And an image feature is a matrix, is a 2-dimensional. And also for each node, it potentially has some features we want to consider, such as the population, economic, or maybe even the temperature or climate information. It really depends on your task. But the features of each node can also be a different dimension. And again, and also the edge is also something we cannot ignore. Like if we think about how the nodes are connected, let's say this is a road segment, there potentially have an elevation change between the 2 nodes. That will impact if you decide to build a road between these 2 nodes or not, right? So of course we have these edge features. If we look at these different types of features, we will realize that they are rarely multimodality, meaning that they have different dimensions, but traditional AI learning, the traditional neural network, it requires you to have a same dimension. It can only process a single dimension data, especially if you're thinking about image processing neural network like convolutional neural network. It's only like 1 dimension. Oh, I'm sorry, it's only a 2-dimension. You have to make all the image to have the same size, same length, same width, and height. So in here, we really want to develop what we call the generic. What we want here is we develop a generic multimodal spatially graphed neural network. The generic here meaning that we can process the model with any types of features, with any dimension features. The multimodal here is that even with different types of features, we have a way to fuse the multimodality. We can fuse the information with different dimensions. And the spatially graphed network is that we highlight the spatial correlation between the nodes rather than something like the social media network or reference network that the nodes do not have any spatial meaning. But in here, in our world, the nodes will have a spatial meaning here. This is also a very flexible framework, because if we only consider that we can ignore the edge features and only consider the node feature, and then we can convert it into a regional spatial graph convolutional neural network, which is only considers the node features. We can also remove the node features from the framework and only keep the edge features from the neural network, and then it can be an edge spatial graph convolutional neural network, convolutional network, so we don't have any node information. The key idea of this one is that we use shallow neural networks to process each feature first, and then in the graph message passing process, we first fuse the data as the output message, and then we do the next stage graph convolution. So it's a bit so what we do, how we achieve that is that we are not using the graph convolutional neural network. We write the convolution process, but during the convolution process, we insert different types of shallow neural networks to process the features first. Yes, I hope that makes sense. Anyway, so in order to test our model, in order to test our developed framework, we synced edge connection prediction as our validation method. So the idea here is that we are assuming we know all the information about nodes. And we are deciding if two nodes should be connected or not. There are really not much engineering motivation behind that, but in the network theory, predicting the connection patterns or prediction if two nodes is connected is a widely used method to justify your method or evaluate your method. So what we do here is that we have our training set, we have our testing set. We use our training set and then train a neural network framework that proposed like here, and then let this train the neural network to predict the connection of our testing set. So then we compare the predicted connectivity of connection with our original testing data. That's it. So in here, we consider two types of networks. The first is the New Jersey Power Network. We train our model with a given New Jersey Power Network map. And then we let it to predict the Connecticut Power Network structure. The second case study is that we give the Oregon River Network, which is a streams network, to train our neural network, and let our neural network to predict the connection of California River Network. So the reason we select this is that Connecticut is very similar to New Jersey, and California and Oregon share the similar weather scenario. So we don't want to make it super difficult because we just want to see the capability of the model. So our results is actually quite promising. Let's say this is our river network prediction results. As you can see, our proposed method achieved the highest accuracy. Remember, we use the Oregon river streams to predict the California river streams. So the model have never seen the California. The model only sees the Oregon's river streams, and you can see it achieved the highest accuracy. It's actually very interesting that if you look at this each spatially graph convolutional neural network, they too achieve the very similar results, giving us implication that the river network is actually more relevant to the features along the edge rather than the features of the node, which makes sense because the river theoretically can only flow from the higher location to a lower location. And if we look at the power network, our proposed generic algorithm still achieved the highest accuracy, but then followed by the regional spatially graph convolutional neural network, which only considers the node features. So as you can see, like for the power network, the node features is actually more important, like how many people are living there, what is the social economic, and what is the regional elevation change compared to only considering the information along the edge. You probably also see this GraphStage. If you are familiar with the graph learning, GraphStage is more like a benchmark model that widely used for the graph convolutional neural network. So this is not specifically, conventionally, it cannot be used to process all the features. You have to brutally concatenate all the features into a super long vector and let it to learn. So apparently, it is not as accurate as the method we proposed. Here, the GraphStage, in the first case study, the GraphStage is also not performing better than our method. Yeah, so I think my time is just right here. So I just want to have a quick overview about our work. In previously, we are talking about first what AI can do for the infrastructure systems, that it can help us make decisions. It can help us explore how to do the asset management. But on the second part, I want to highlight the fundamental is about how we can train the artificial intelligence to really let it learn better than just using an established algorithm. So in conclusion here, I want to highlight that first, we say that the reinforcement learning can really to make the decisions under complex and uncertain scenarios. It is also transfer so that it can be pre-trained before the hazard. The second thing is that the second part about the learning representation is that we find a way to better learn the network pattern or network representation by the neural network. And this even more advanced graph neural network can be used for a wide application. For example, if we combine this advanced graph neural network into the reinforcement learning, it potentially can give us a better decision. Or if we combine this advanced graph neural network for, let's say, state estimation or condition monitoring, it also potentially can give us a more accurate prediction. So it potentially can be used for a wide application, depending on, because essentially it is a network representation learning. You can add other decoder layers of the neural network and convert it to solve different network relevant tasks. I hope these two components make sense, and also I'm looking forward to have any questions. I just want to give a quick introduction about our group here. We are from the University at Buffalo, so we are really focused on the urban water scenario. Although many methods can be generic to the other infrastructure, especially the transportation or power systems. But we really want to see how we can, starting from the water and trying to see how the water and other systems interact with each other. So yeah, with that side, I think I'm happy to take any questions, or Jiran, if you have any comments.
Thank you, Dr. Fan, for the very interesting presentation. You showed us how AI can be applied to resilience optimization and network science. The technical details of the neural network you presented was very insightful. So we have about 10 minutes for questions. Is there anyone have any question for Dr. Fan? Okay, I have a question actually for in the first part for the resilience optimization, you embedded a graph neural network with to replace the traditional fully connected neural network. Did you run a comparison about performance of like with graph neural network and without?
That's actually a good question. The reason we actually didn't run that is because we don't know how to input a networked system into normal neural network. If you remember that a normal neural network, it takes the input neurons, and theoretically it should take the vectors as inputs. But if our system is a networked system, and each node will have its own features, and the only feasible way that I can imagine is that concatenate all the nodes features into a super long feature and put it into a fully connected neural network.
Yeah, actually, that's what I did in my research. I didn't use the graph learning, but I used the feature of each node or edge and combine them as a very long vector as the input. So I'm very curious about the performance of the two methods.
Yeah, because when I was thinking about this approach, I don't know which node should be first and which node should be the second. Like, I'm not sure if the order matters or not. And so eventually we decided we'll just use the graph-based method, so I don't have the trouble like that.
Thank you.
Yep.
Anyone have any other questions? I think your presentation is very clear, so they don't have any questions.
We have like a lot of students here. I guess we are.
Oh, there's one, but he does not have
they don't have the
grant.
Yeah. Yeah, I think we are default muted.
Okay, Jason, you should have access to mic. And also Yunhan.
Yeah, I don't actually have much of a question, but I can see how this can be applied maybe to certain parts of structural applications. Have you guys ever considered for buildings or forensics using the AI to model buildings? I know it's definitely far out of the wheelhouse of the current applications you guys observed, but
So can you repeat what application did you just mention?
more of a structural. So with like forensics analysis of buildings, certain columns or
Yep.
the like could be. Could you apply a neural network and I'm guessing a similar-ish way to that?
Yeah, so one thing that we are thinking about is to using the graph neural network to mimic the behavior of the meshed simulation. For example, if we think about the finite element simulation or many like fluid dynamics simulation, when we do the simulation, we mesh the system into a network, and then we do all the governing equation and differential equation solving them. So we do have thinking about how we can use a graph neural network try to mimic the behavior of this meshed system and see if it can work with this finite element simulation, something like that. I'm not sure if it makes sense, but we think it would be a good approach. It would be a great approach for the surrogate model.
Okay, Yuhan.
I think
do you have a
you're
question?
muted. You can unmute yourself.
Oh, okay. I have a question about you define the policy as one step to fix one road or one segment, but did you considering fix the road parallelly, or what more policy will cause the I mean, did you consider more like policy to fix the scenario?
Yeah, I think that's something that I have been asked before. It's like currently we are assuming at each time we only have one maintenance team. So like each time we only fixed one location and we do this sequential modeling. But in theoretically we potentially have multiple repair team and we will do the multiple decisions. We may fix multiple parts at the same time step. So one solution that I am thinking about that is we have a multi-agent reinforcement learning. So basically each agent represents a repairing screw and a repairing crew, and they collaborate with each other. Or there is also a more centralized multi-agent reinforcement learning trying to assign the tasks to multiple repair crews. I think that's a main limitation. That is one thing that probably very promising in the future is to really consider this multi-repairing group into an optimization process.
Okay. And when you train the model, did you add some like the extra episode reward, or you use the immediate reward to compute the loss?
We use the this equation. So if you see here, when we train the model, we are considering the future reward and also the instant reward. So there is a if you look at the Bowman equation here, there is a reactor. So it takes the instant reward, which is immediate reward, and also the potential reward that this action can lead. So in my setup, I gave like half 0.5, 0.5 weight to each part. So the decision is trying to balance the immediate reward and also the long-term benefit.
So when you define the reward, will it affect the like final policy? Like if you give different weights.
Different weights. It's possible. It's possible. So we did a little sensitive analysis, but we later realized that still 0.5 is relatively better, but it really does not impact a lot, to be honest.
Oh, okay. Thank you.
Yes.
Hi, Xudong. Thank
Hi.
you for the wonderful presentation.
Yep.
Really learned a lot from this short presentation, and I'm curious, like, agentic AI is a very fancy word here, and for our students, can you envision a little bit about the potential use of generative AI or agentic AI for the same problem?
Yeah, actually, we think it would be a great direction, to be honest, because right now what we are doing or previous doing, we are trying to find the mathematical level optimization, right? Like we mathematically model the system and we use the computer to solve the optimal decision. However, we really didn't consider many real world constraints, like the regulations, the standards, or the team coordinates, or the codes. So we think that in the long term, it is very promising that we combine everything together by using an agent. Like for example, part of the agent may be trying to find this mathematical solution, the other part trying to understand the regulations or trying to understand the resources, and maybe the other part trying to understand the human behaviors. And together, they provide a more realistic decision support rather than we just looking at from the mathematical perspective. I hope it makes sense. Like,
yeah, interesting, definitely.
Yeah.
So, yeah, I like the point that an agent may be able to consider more regulatory or policy level constraints. So, other than that, what else do you think a generative AI could possibly perform better in this scenario compared to the more traditional approach here? Is there any other like exciting edges or advantages that will motivate you or our students to pursue?
So I attended a few like AI workforce organized by AIC recently. One thing the AIC leadership is very interested is we call it knowledge transferring or knowledge tokenization. So it's basically like they want the AI can support the decision all the knowledge by the existing books, codes. Again, it's all regulatory. So how are we going to embed the existing codes, design standards into either maintenance or into the design or into the emergency management is relatively important. And I assume to incorporate this type of knowledge, we still probably need to use a generative AI to help us better understand these books, right? And I would say another generative AI is very good at is human behaviors. It is you can try to let it mimic the human behaviors, which is also very important.
Okay, great. Yeah, thank you for your insights.
Yes.
Okay, so we have reached 1 p.m. and if there's no more question, thank you again, Dr. Fan, for the wonderful presentation and for all the
Professor?
Yes.
I have another question.
Okay, go ahead.
Yes, because in like civil domain, we not only consider the final results of like PDW we talked in the slides. We're also considering the for example the equality, and we want to protect the main area, like we want to fix some domain's infrastructure firstly. So if we add this result into the final goal, so will this method also works?
The equity and the inclusive. I'm not sure if, well, I'm not sure, like, at least at the current, yeah, I think first it is important, although it is not like a focus of current administrative, but that is still an important issue. And like I said, if we really want to think about anything that is related to human behaviors or social science side, or like this part that traditional mathematics is very difficult in modeling. Large language model, especially the foundation model, I would say is a very important part for this task. Does that make sense?
So this method also can be applied to considering more about the
I would say it should be combined with foundation rather than directly working on the reinforcement learning. It should be combined like the agentic system we just discussed. Well, can we integrate the foundation model into the reinforcement learning? Maybe that potentially can also be a direction.
Oh, okay, thank you, President.
Yeah.
Okay, any other questions? Okay, thank you, Dr. Fan, for joining this seminar.
Yeah, thank you for the invitation.
So,
thank you, Dr. Fan. We look forward to having you in person next time. And best wish, good luck for your family.
Yeah, next time when you are visiting the Niagara Falls, welcome to, please let me know, and
sure,
we can catch up. Yes.
All right.
Right.
Happy Friday and have a nice weekend for everyone. Thanks for joining us. See you next time. Thank you. Bye-bye.
thank you.
Bye-bye.
Bye.